Hi, welcome to this last video in machine learning. Today we are going to look at, well, our final topic, and that is about regression trees, backing, boosting, and random forests. I would say that this is a list of, well, very fancy names in order to describe maybe what we could say the best or most powerful tools that we have these days in machine learning. Before I'm going to say anything about this, I have to say that officially the only method that we're going to look at today, which is really going to be a prediction algorithm, is going to be regression trees. Regression trees is a method in order to predict, as we have seen many methods in machine learning and supervised machine learning. That is actually the goal in supervised machine learning. We should realize that the other methods that we have over here, backing, boosting, and random forests, are actually not themselves methods in order to predict. However, what they are is that they are methods in order to improve other prediction methods, where backing and boosting are going to be methods that are going to, can be used for any kind of method, and random forests, well, these can only be used for regression trees. That brings me back to these regression trees. Regression trees, as I already said, are methods in order to predict. They're algorithms in order to predict, as many other algorithms that we have already seen before. However, we should realize that regression trees by themselves are actually not that great predictors. We're going to use simple regression trees. Then at that moment in time, regression trees usually are not that great predictors. And the main reason behind that is because of the fact that their variance is very high. So therefore, what we typically do is that we're going to not use regression trees, but we're going to improve regression trees by any of these methods that we've over here. And improving these regression trees by these methods that we have over here can make regression trees one of the most powerful methods in order to predict. But that, of course, brings me once again back to these regression trees. Well, I can say a lot about these regression trees and say the first part of this video is going to be completely about these regression trees. First thing I can say about regression trees is that they are methods that divide the feature space, I would say the total support of our features, into rectangular and disjoint subspaces. These are usually called p-dimensional cuboids. Well, what does that mean? Well, that means that, for example, at the moment that p is going to be equal to 1, well, then what we're going to have is that we're going to divide the support of our single feature that we have over here into different intervals and disjoint intervals. At the moment that p is equal to 2, well, then what we're going to get is that we're going to get these rectangulars that we have over here. If p is equal to 3, then we are going to have cubes. And in the very general case, we are going to have these p-dimensional cuboids that we have already been talking about before. You should realize that these things are not going to be only disjoint, but they're also going to cover the whole support with respect to our feature space that we've over here. Well, and then within any subspace that we're going to define, we simply give all the observations exactly the same prediction of the outcome. So that means that if we have two, axes that we have to predict, then at the moment that they are in exactly the same subspace, then they're also going to get exactly the same prediction. Of course, if they're in different subspaces, then they can have completely different predictions. But if they're in exactly the same subsample, subspace as we have over here, then at that moment in time, we are going to have exactly the same prediction. More in particular, suppose that we have m different subspaces and define the mth subspace by this Rm that we've over here, well, where little m runs from 1 till large M that we have over there, well, then the only ingredient that we're still missing is, of course, this prediction that we're going to make per subspace. Well, let's call that equal to Cm. What are we going to get then? Well, then our prediction function, gx, that we generally have, can then be simply written as, well, gx is equal to C1 in the case that x is an element of R1, so of the very first subspace. Gx is going to be equal to C2 at the moment that x is an element of R2. gx, of course, is going to be equal to z3 in the case that x is an element of R3, etc. Well, then you should realize that writing it down like this is, of course, very straightforward, but it's a little bit long, of course. So therefore, we typically are going to write this a little bit differently. What we're going to do is that we're going to look at a particular sum. Here we are going to have a sum over all the different subspaces from 1 till this large M that is over here. And then we're going to use this indicator function that indicates in the case that X is an element of Rm multiplied by Cm. Well, this is exactly the same as what I already said before. The reason behind that is because of the fact that even though we have here a full sum, you should realize that there's only one subspace Rm for which X is going to be an element. And the reason behind that is because of this assumption that we've made over here. These are disjoint subspaces. So that means by definition that at the moment that X is going to be, for example, an element of R5, then it cannot be an element of R10 as well. And the reason behind that is because of the fact that the definition of disjoint subspaces means that these subspaces R5 and R10 cannot have common elements. That is what disjoint means. So that means that in this particular case, we know for sure that there can be at most one, say, subspace that we have over here for X to be an element of that particular subspace. But as I already said as well, we're going to assume that the subspaces that we have over here are going to cover the whole feature space. So the whole support with respect to our X's. And that means not only that there is going to be at most one, say, subspace for which X is going to be an element, but there's exactly one subspace for which X is going to be an element. Well, then it's not that difficult to see that the way I defined it over here is exactly the same thing as what I just said with respect to saying that Gx is equal to C1 in the case that X is an element of R1, etc. Then, of course, the question still arises, how are we going to determine this Cm step over here? Well, on the next slide, I will do this theoretically, but we should realize that in the end, in applications, we're going to try to do this as simple as possible. We just want to give this CMs, well, very simple rules with respect to prediction. We can, for example, think of the majority vote in a classification problem. So what does that mean? Well, then what we're going to do is that we're going to look at a particular subspace Rm that we've over here, and we're simply going to set Cm, well, equal to the class that is most frequent in this particular subspace. That is what we call the majority vote. But we can also think of a situation in which we are going to have a continuous outcome variable. And then in that particular situation, we're simply going to take the average per subspace in order to determine this Cm that we have over here. But let's now look a little bit more at the theory. What we should realize is that what we usually would like to do is to find among all these, say, potential functions that can be defined by this function that we have over here, we would like to get the best one. And what is that? Well, that's always the same in machine learning. That is the one that is going to minimize the so-called theoretical risk. Here we have another time our nice theoretical risk, which is nothing else than the mean of our loss function. Well, then what we can do is that we can, well, essentially try to find R1 star to Rm star and C1 star till Cm star that is going to minimize this, say, theoretical risk that we have over here. I'm not sure whether this is the usual notation used in many statistical books. I'm pretty sure that it might not. But what this actually means is that if I'm looking for my G star, then at that moment in time, I'm going to try to find an Rm for any class and a Cm for any class. That's going to minimize this theoretical risk that we have over here. Well, now we should realize that we cannot do this. This is infeasible. The reason behind that, I have already said that a couple of times before. That is essentially because of the fact that we do not know the distribution of y and x. Therefore, we cannot calculate this mean that we have over here, and therefore we can also not minimize with respect to that mean. And we do already know why we don't know this joint distribution of y and x, because of the fact that that is what we typically call the data distribution. And one thing that we typically assume in statistics is that we do not know the distribution of our data. So therefore, we are going to do something instead. The trick that we are going to use is always the same in machine learning. And that is that we, instead of using the theoretical risk, we're going to use the so-called training risk as we have defined it over here. So therefore, we're going to look for R1 hat till RM hat and C1 hat till CM hat. That is going to minimize this training risk that we have over here. And you should realize that that is what we always do in any kind of supervised machine learning method. We should realize that at the moment that we're going to estimate our parameters of the model, that we usually call that the training stage, then what we do is that we're going to minimize our training risk. Ordinary squares does that. So the betas of the ordinary squares are going to minimize the so-called squared loss function that we've over here, the sum of squared residuals. That is by definition the training risk in that particular case. And any other method does exactly the same. So we should realize that, for example, nearest neighbors does this, but also local linear regression does this, and anything else. Like, for example, at the moment that we're going to look at ridge regression or at the lasso, also these are going to minimize the training risk with respect to the parameters that we have. So that is what we do over here as well. Well, at least theoretically, what we would like to have is an R1 hat up to an RM hat and a C1 hat till CM hat that is going to minimize this thing that we have over here. Can we do that? Well, I will say much more about this later on, but the first thing that we need to do, of course, over here is to substitute in our G function that we had at the previous slide. So what we can do is simply substitute this G function that we had at the previous slide. And then what we have to do next is that we have to determine the loss function. However, we do already know that that actually depends on the situation in which we are. If we are in a classification situation, if we would like to do classification, well, then we do already know that the loss function is going to be this famous 0,1 loss function. So then our minimization is going to be this thing that we have over here. For any kind of, yi and xi that we have over there, we're going to minimize these things over here with respect to this, say, loss, or maybe better to say, the training risk that we have over here. At the moment that we're going to have a continuous outcome variable, then we do already know that we have to use this quadratic loss function, and therefore we're going to get this risk that we have over here, this training risk that we have over here. So generally speaking, what we have to do is, for any case, we have to simply minimize this thing that we have over here. I'm coming back to that later, but before I'm going to do that, well, one thing that you might already have recognized is that the way we have described so far regression trees is much like the way we have been describing another estimator, and that is nearest neighbors. Remember that with respect to nearest neighbors, at the moment that we're going to predict, then also what we actually do is that we're going to look at an area. We are going to look at a subset of the total feature space. More in particular, what we do is that we're going to look, at least in a two-dimensional case, we essentially look at a circle, and we're going to make the circle as big that we are going to cover in a sense with respect to the axis. We're going to cover all those, say, observations, all those k observations that are nearest to the point that we would like to predict. That's what we actually do at the moment that we are going to do nearest neighbors. The reason why we have a circle is because of the fact that we typically are going to look at the Euclidean space, or the Euclidean distance. And that means, of course, that we are going to have a circle, at least in the two-dimensional case. If, say, the feature space is going to be two-dimensional, in a higher dimensional case, we're going to have something like a sphere. But the idea is exactly the same. What we're going to do is that we're going to have an area, and in that area, we do exactly the same thing as what I described at the previous slide. Then what we either are going to do is that we're going to look for the majority vote in that particular area, or we're going to look at the average at the moment that we're going to look at a continuous outcome variable. But we should take into account that there are important differences between nearest neighbors and regression trees. In the end, regression trees are quite different from the nearest neighbors. And that's especially because of this first thing that we have over here. We should realize that in the case that we're going to look at regression trees, then we minimize instead of simply choosing the area that contains the k nearest neighbors. Another way of saying this is that you should realize that at the moment that we're going to look at k nearest neighbors, then at least in the so-called training stage, at the moment that we're going to estimate parameters, should realize that k by itself is not really seen as a parameter of the model at that stage. What we have to calculate is, of course, are these, say, well, averages or majority votes in order to predict. But at the moment that we're going to look at the training stage, then we are not going to determine this k that we've over here. At the training stage, you do not determine this k. This k is going to be given in nearest neighbors. And that's quite different from regression trees, because you should realize that here it's actually written down. Even in the training stage, what we're going to do is that we're going to set our R1 till Rm and C1 till Cm in such a way that the training risk is going to be minimized. So this is actually much more complex as what we in fact have in the case of nearest neighbors. Of course, true even in the case of nearest neighbors. At the moment that we get to the so-called validation stage, then we're going to make a choice with respect to our models, our different kind of models, and then we should realize that then we are going to make a choice with respect to this k that is over here. But here it goes even a little bit further. Here, even in the training stage, we're already going to make a decision about these areas that we have over here, not only about these things that we have over there. Well, there are actually other differences between regression trees and nearest neighbors. These are less important, but first of all, you should realize that subspaces in regression trees, they are so-called rectangular rather than circular at the moment that we're going to look at nearest neighbors. I already said that in nearest neighbors, you should realize that you have a circular space, and that's actually not true in regression trees because they're always going to be rectangular. In addition to that, we should also realize that the areas are always going to be disjoint, whereas they are going to be overlapping in nearest neighbors, at least at the moment that k is larger than 1. Remember that what we actually do is in nearest neighbors is that we're going to look for the, say, k observations that are nearest with respect to x. And you should realize that if we then have two different x's that we would like to predict, well, then of course, the first x is going to have a particular area in which you have the k nearest neighbors. The second one, if it's going to be very close by, is going to have an area which is almost identical. It's not exactly the same, but it's going to be almost identical. And that is not the case at the moment that we're going to look at regression trees, because there they are by definition always going to be disjoint. Now you should realize that even though I said in the previous slide that what we ultimately would like to do, well, I would say better say ideally like to do, is that we're going to determine these things that we've over here by minimizing this training risk that we've over there. Well, that is actually going to be quite easily infeasible. It doesn't have to be infeasible in the case that m is going to be really, really small, and at the moment that n is not going to be that large, and probably also xi is not going to be very highly dimensional, so p is not going to be too large. But you should realize for, well, typical applications that we have over here, that where m and n as well as p are not going to be really, really small, well, then in that particular situation, this could be ridiculously difficult. And the reason behind that is because of the fact that we should realize that what we do here is that we set all the r's at exactly the same time. And you should realize that, of course, in a particular feature space, there are many, many r's that we can actually choose among. So that makes it really infeasible just to try to, say, find the combination of the r's and, of course, the c's that we have over here that is going to minimize this thing that we have over here. So therefore, what we're typically going to do is that we're going to introduce heuristics in order to obtain a near optimal solution of the minimization problem. Well, and therefore we're going to make a couple of restrictions. And the first and main restriction that we're going to make is that we are going to do the division sequentially and break up the spaces into only 2 disjoint spaces. So what does that mean? Well, that means that at the moment that we're going to be in the very first stage, well, then we have our our complete feature space, of course. And then what we're going to do is that we're going to break that feature space up into 2 different subspaces. Well, then we can actually go to the second stage. Well, in the second stage, we are then allowed to break these, say, 2 subspaces that we already have further into also 2 different subspaces. So that leaves us actually with 4 different subspaces. Well, then after that, we can go on, and in the third stage, we're going to have 8 different subspaces. In the fourth stage, we're going to have 16, etc. So that's the idea that we are now going to have. The question now arises how this is going to work in the case of our example. Remember that we had this classification example where we had on the x-axis different levels of x1, and on the y-axis we had the different levels of x2. And also remember that we had this optimal decision boundary that we had over here, and that implied that the optimal predictor was defined as follows. At the moment that we are in this area that we have over here, then it would always be better to predict blue. And at the moment that we are going to be either in this area or in that area that we have over there, then it's always going to be better to make a prediction that is going to be red. But well, generally we assume that we do not know that, and therefore we're going to use algorithms in order to predict it. Let's now look at how this actually works with respect to trees. Well, then what we're going to do is that we're going to start with our first stage. And the first stage means that we're going to have our whole feature space over here. So we're going to have all of our observations over here. And what we now have to do is that we are going to essentially break up this feature space into 2 different subsets. How are we able to do that? Well, we should either do this with respect to either x1 or with respect to x2. At least we can do this with respect to both of our features. What we should take into account that the restriction is going to be is that we're going to do this rectangularly. So that means that either we're going to do this vertically, so we're going to make a vertical split, or we're going to make a horizontal split, as we can do over here with respect to x2. That means already that we cannot do this diagonally. For example, this thing that we have over here, or we cannot do it something like that. We always have to do this either fully, say, horizontally, or we have to do it completely vertically as we have over here. Now, of course, the question arises, if we have these kind of restrictions, what is then going to be our optimal breakup that we have at this very first stage? Well, what I've done is that I've asked Python to do this for me, and Python actually said that it would be best to break it up as follows. We are going to have here a level of 1.217, as we will later on see, with respect to x2. And that means that we're going to have now 2 different subspaces, one for which x2 is smaller or equal to 1.217, and another one for which we are going to have larger than 1.217. But we immediately see that in that last one, well, most of the observations are red there, so there it's going to be best to make a red prediction. At the moment that we're going to look at this lower one that we've over here, well, there maybe a little bit more difficult to see over here, but there most observations are actually blue, so therefore there it's best to make a blue prediction. So that's how we're going to do this in the very first step. Well, now, of course, the question arises, you have been already, or I have already been talking quite a lot about trees, but I haven't shown you any tree yet. So the question arises, why are these called trees? Well, that's because of the fact that you can see this as a so-called decision tree. The way in which I actually have split up the total feature space as we have done right now can be described in a very simple decision tree as we have it over here. In this case, there's only one decision to be made here in the root, and that is whether x2 is smaller or equal to 1.217. If that is going to be correct, then we are going to be here in this true that we have over there, and then in this picture we are here at the bottom. And then it's best to make a decision that we're going to have a blue prediction. And at the moment that we are going to have that this is not correct, so at the moment that x is not smaller or equal to 1.217, but then we are in this area that over here. And then based on this tree that we have over here, then we are going to make a red prediction. Well, that is exactly the same as what we have over here. Well, now a question that arises is whether we do very well with respect to prediction. Well, the obvious answer with respect to this is that this is actually a horrible prediction. This is even much worse than any of the predictions that we have made in the previous lecture, in the previous video, because of the fact that there, well, the worst predictions that we had were linear regression without any higher order terms, but that was still much better because then we got something like this instead of this thing that we've over here. This is even much worse than what we have done before, the worst things that we have done before. But of course, this is not the end. What we can do now is that we can extend this. What we can do is that we can make further breakups. We can just add another layer to our tree. That means nothing else is that we are now allowed to break up this area that we have over here into two different areas. And we are allowed to break this subspace that we have over here into further subspaces. So then we can ask, Python again. Again, we should realize that this could be for any area, either being, well, vertically in this way that we have over here, and it can be horizontally in this way that we have over here, but again, it has to be rectangular. Well, now again, I have been asking Python with respect to this, and if we're going to do that, well, then we are going to get this picture that we have over here. Now we actually see that Python now has, subdivided this lower space that we have over here, the larger space that we had. Well, it has now subdivided it with respect to x1. That's not necessary. It's not the case that we start with x2. So the first, say, split up with respect to was with respect to x2. Then now it has to be with respect to x1. That's not necessary. But we see here, and that is actually the case. We have now that Python has been splitting this up in terms of x1. So vertically, and it's at this level that we have over here, somewhat in between 0 and -1, say at -0.4. And then at the moment that we're going to look at the upper subspace that we have over here, well, then we are going to see that Python actually has done it also vertically, also with respect to x1, but the value of x1 is a little higher. It's roughly equal to 1 in this case. Well, then we now have 4 different areas. And now we have to determine, of course, which areas are going to be red and which areas are going to be blue. Well, again, we are going to do that on the number of observations that we have in every area. This area is completely red, so it should be also red. This area is almost completely blue, so therefore it should be blue. Well, these areas are a little bit more difficult, but this one is quite red, so therefore, well, it's better to make the prediction, of course, to be red. And this area that we have over here is now going to be a blue area. Well, that means that now in terms of our tree, the tree now is already going to look much fancier. It now looks like this one that we have over here. So we now have here, first of all, at the moment that we are over here, that means, of course, that we are in this lower area that we have over here. And then at the moment that x1 is smaller or equal to -0.401, well, then at that moment in time, we're going to end up over here in our picture. That's, of course, this area that over here. And then according to this tree, we're going to make a red prediction. Well, if that is not going to be true, then we go in this direction. That means, of course, in this picture that we end up over here. And then at that moment in time, we are going to, well, according to both the picture and, of course, the decision tree, we're going to end up over here, make a prediction equal to blue. But we can also be in this branch of, say, the tree. And then in that particular situation, what we're going to have is that we have to look at whether x1 is smaller or equal to 1. So generally, we are now in this subset over here. But if x1 is now smaller or equal to, well, 1.082 or 1.082, well, then at that moment in time, we're going to be in this area over here and we make a red prediction. Otherwise, we're going to make a blue prediction as is done over here. But now what we can do is that we can make further split ups. Well, in principle, this means, of course, that we're going to have, well, at least in theory, 8 different new, well, in total, 8 different spaces. We should realize that it's not always that great to do a split up. It's not always necessary to do a further split up. For example, at the moment that we're going to look at this area that we're over here, why would you ever split this area up? The reason why I'm actually asking that is because of the fact that we should realize that this is what we typically call a pure node. All the observations in our training sample in this node, in this area that we're over here, they're actually red. So therefore, we should realize that I can do a lot of split ups, of course, here or there, or can do it here, further horizontally. I can do it everywhere, but we should realize that after I've done the split up, both areas are still going to be red. So therefore, there's not going to be any difference with respect to the predictions that I'm going to make. Of course, that is not true for any of these areas that we have over here. This area, well, most likely going to be split up. This one probably as well. But we will also see that this one is not going to be split up. And the reason behind that is not because of the fact that in this case we have a pure node. In this case, we do have observations which are blue in this area that we're over here. But we should realize that it is going to be very hard to do a split up over here that will in the end result in both a blue and a red area. For example, what I can do is do a split up, for example, over here, somewhere around here. But then you should realize that both areas are still going to be red, and therefore there's no difference with respect to our prediction. So therefore, in the end, what we will see is that only this area and that area will be split up at the moment that we asked it Python to do that. So then we are going to see that, well, this area is going to be split up. We're going to have it here, in this case, horizontally. But we have then here a pure node, only one observation, by the way. And here we have almost a pure node, only one red observation here, over here. And then in addition to that, what we're going to see is that this area is going to be split up. And we're going to see that that is going to be split up in, well, in this case, vertically in this situation that we've over here. So we get a blue area here and a red area now over there. And then finally, if we're going to then look at our tree, well, the tree now is going to look like that. Take into account that we have 2, say, areas where we're not going to make any further decisions, but we have these 2 areas in which we still are going to make a further decision. That leaves us with the question of how will we now actually predict with respect to this particular tree? Well, I would say actually quite good. With this tree of a depth of 3, there are 3 different layers. We actually do already quite well because of the fact that even though there is still a difference between the optimal decision boundary and in fact the decision boundary that we have now, which is defined in fact like this one that we've over here, we should realize that the difference is not that big anymore. In addition to that, at the moment that we're going to look at our, say, test risk, then the test risk is equal to 0.213. That means, of course, that our misclassification in this case is going to be 21.3% on average. That's not that far anymore from the, say, 18.6% that we actually can get at the moment that we are going to have our best predictor. You realize that we haven't done any cross-validation yet, and with respect to that, we have only seen the nearest neighbor to perform somewhat better than this 21.3% that we have over here. So therefore, we do already have now quite a good predictor. Well, that brings me to the next topic, and that is the topic of, well, so far we have been, of course, looking at regression trees already. But what we have done so far is that I simply have asked, well, Python to do it for me. Well, that's essentially what you should do as well for any kind of tree. The building of a tree is not that simple, but we should also take into account that we have to know a little bit about how to build a tree. Well, generally we then have to make a couple of different decisions. First decision that we have to make is what should be the simple predictor per subsample Rm. The second is, the second question that we have to ask is how do we split nodes into further subnodes? And then the final question that we have to answer is how large are we going to make the tree? Well, what I'm going to do is I'm going to focus here on the first two questions, especially on this one that we have over here. I'm not going to say too much about this third question that we have over here. In terms of depth, what we're going to do in the end is that we're going to use cross-validation with respect to that, as we usually do. However, you should realize that even at the moment that you already have depth, then the question sometimes arises, should we actually make further split ups in particular kind of nodes? Well, that's a thing that is well described in the book, so therefore I'm not going to talk too much about that. I'm going to focus on these two things that we have over here. That brings me, first of all, with respect to the first question, what should be the simple predictor per subspace Rm? Well, again, that actually depends on the setup. And actually I already have said or talked about that. That is to say that at the moment that we're going to look at the regression problem, so in the case that yi is continuous, well, then we're going to use the average in the subspace Rm. So exactly what I said at the very first slide. So then Cm hat, so the estimator of this thing that we have over here, is nothing else as the sample mean in a particular subset, in this case, this subset Rm that we have over here. So that means nothing else is that we're going to sum over all the observations with respect to y in that particular subset, and we divide by the number of observations that we do have in that particular subset. At the moment that we're going to look at classification analysis, well, then we're going to do something else. Then, first of all, what we're going to do is that we're going to look at the relative frequency that we have in every subset with respect to the classes that we have at hand. So therefore we're going to define this p hat mj that we have over here, which is nothing else as the sum of the, say, observations that belong to this class j that we have over here in this particular subset that we have over there, and then again divided by the number of observations that we have in this particular subset. We can interpret these things that we have over here essentially as estimators of probabilities of the different classes within a particular subset. And well, then what we're going to do is that we're going to predict that particular class in that particular subset that is going to have the highest p hat that we have over here. So we're simply going to do this for any kind of subset m that we have over here. Well, that brings me to the second question, and that is, how do we split up nodes into further subnodes? Well, what we're going to do is that we're going to go for a so-called greedy approach. We have already looked at greediness before, at the moment that we were looking at forward states-wise regression. Then what we did was that we looked already at greediness. That meant at that stage that we are just going to include one, say, variable at a time in a particular regression. Well, in this case, greediness means that we are only going to, well, do one particular split at a time, as we already have been looking at, but our decision is going to be based just on one step ahead. So greediness in general means that we're only going to look one step ahead. So we're not going to do what typically chess players do at the moment that they are going to do one particular step. Then they already are going to think about the steps ahead that we are going to have. Greediness does only mean that we look one step ahead, and also we do not look backwards or whether some of the steps that we have made in the past could actually be improved. Well, that means in our case that we're going to split up the nodes into further subnodes in such a way that we're going to have the minimum training risk in fact, that particular subset that we were looking at. So that means actually nothing else than that we are going to look at the potentially largest reduction in terms of the training loss. For that, what I have to do is that I can look both at classification as well as regression, but let's first of all look at a regression context. Well, then what we can do is that we can look at a particular subspace Rm, and we're going to ask ourselves the question, how can we, well, split this up the best in two different, say, subspaces that I'm now going to call R1m and R2m. Sometimes it's best to think about, well, this to be the left hand and this to be the right hand. Actually, think that in the book even this is going to be called L and this is going to be called R or something like that. But generally, we simply are going to think about R1M and R2M. Take into account that there are many potential ways in which you can split up this subspace that we've over there. Therefore, we are going to introduce this R1MJS that we've over here, which is a function of both J and S, and which is going to describe these, say, spaces, these subsets that we've over here. At the moment that we're going to break up a particular subspace into two different subspaces, then we should first of all realize that we can do that on any kind of dimension. Take into account that at the moment that we had in our particular case, in which P was equal to 2, we had two different features, then we could have done that actually vertically, and we were able to do that horizontally. That is what we have seen all the time. Well, more in general, at the moment that we have P different features, then we can do that along all the dimensions. So therefore this J that we have over here actually describes for any potential subspace that we're going to have, any, say, potential slicing that we're going to have with respect to this subspace that we have over here, on which dimension we're going to do this. So this J can actually only take values 1, 2, 3, up till this P that we have over here. And this means actually that we are going to do it, we are going to slice, in fact, on a particular dimension J that we have over here. Well, then, in addition to that, well, apart from deciding on which dimension we are going to slice, we should also take into account that the breakup should also be done at some particular place. So apart from the dimension, we should also take into account that we could actually slice it on different, say, places. That's also what we have seen in our case. At the moment that we're going to, well, already decide that we're going to do it, for example, vertically, then of course we can do the slicing over here, but we can actually also do it over there. So therefore we should realize that we get another variable S that actually describes where we're going to break up our, say, subspace into two further subspaces. Well, because of the fact that this is going to be rectangularly, this can be simply seen as xj smaller or equal to s for one subspace that we typically call the left hand side, for all the xj smaller or equal to s. So now we have this total, say, set that we've over here, which is nothing else as all those x's that were in the original subspace that we over there, the big one, that for which xj is smaller or equal to s, and then of course the other one, R2mjs, automatically is going to be the rest. So that's of course then all the xj's that are going to be larger than s. These are many different potential subspaces. So then the question arises, how are we going to choose j and s? Well, that is of course as follows. What we're going to do is that we're going to minimize what we could say the remaining training risk that we're going to obtain after doing the further breakup. So therefore here we're going to have the training risk that we're going to get after we have well done essentially the breakup with respect to this first subspace that we are going to have then over here, and this is going to be the remaining training risk that we're going to have with respect to the second subset that we have over here. Well, and then we still have to define this C1 hat and that C2 hat that we have over here, but they are simply going to be equal to, well, exactly as what we had before with respect to the C hats that we have introduced before. This C1 hat now is going to be, well, the sample mean with respect to y in that particular new subsample that we have over here. So it's going to be all those, what we are going to do a sum over all those observations with respect to y in that particular subset divided by the number of observations that we have in that particular subset. And we are going to do exactly the same with respect to C hat 2 as we have it over here. Now for classification problems, we should realize that we cannot use the squared error loss. However, the idea is in principle exactly the same. What we have to do is that we now are going to use exactly the same R1MJS and R2MJS as defined over here, But instead of minimizing this criterion function that we have over here, we're going to use this criterion function that we have over here, where we have replaced the squared error loss with respect to this 0, 1 loss that we have over here. So this looks all quite straightforward. Then still, of course, we have to define then C1 hat and the C2 hat that we have over here. Well, they are going to maximize these P hat 1 mj's that we have over here and the P hat 2 mj that we have over here. Well, and again, the idea behind that is exactly the same as what we have seen before with respect to the P hats that we have introduced before, but now for 1 and for 2. So therefore, P hat 1 mj is going to be the number of observations of class J that we've over here in this new class R1 mjs that we've over here, divided by the number of observations that we have in that particular class R1 mjs as we have it over here. And in exactly the same way, we're going to define P hat 2 mj, and that of course implies that the only thing that we're going to do is that we're going to, well, essentially do nothing else as predict C1 and C2 by those, say, well, classes that are most frequent in the new, say, subsets that we're going to have after having done the breakup. And then again, we're going to minimize with respect to this J and S that we have over here. So it is essentially as simple as that, but we should realize that even though this looks quite simple, you should take into account that it's not that simple. You should realize that with respect to the minimization that we have over here, well, even that is not extremely straightforward, but we should take into account that one of the nice things with respect to this thing that we have over here is that it is differentiable, at least in terms of this C1 hat that we have over there. Well, that is actually not true at the moment that we are going to look at this thing over here. We should realize that this is highly non-differentiable. So therefore, minimizing this thing over here might not be that easy. And therefore, what we're typically going to do is that we are going to use another kind of criterion function. But before I'm going to get to that, what I'm going to do first is that I'm going to rewrite this sum a little bit. And that's what I do in this slide. So at the moment that we're going to look at this sum that we have already seen before, well, then we can do, first of all, we can do some kind of very trivial tricks. First of all, I'm going to multiply this by the sum of the observations that we have in this particular subset divided by the sum of observations that we have in that particular subset. So this is just equal to 1, but then what I can do is also very trivially, I can take this one together with that one that we've over there, and this one I simply leave it in front. And then also another trivial step is that I'm going to take here is that this number of observations in this particular class, I'm simply going to define it as N1 mjs. So then what I'm going to do next is that I'm simply going to write it like this. But now you should realize that what we have over here is, say, the number of observations within this particular class in which we are going to make the wrong, say, classification, in which we are going to make the wrong prediction. Well, suppose that the number of observations that we have in the total class is, for example, equal to 100, and that we make 20 different misclassifications. Well, that's exactly the same, of course, as, say, 100 minus the 80 good classifications that we have. So in general, what we can say is that this thing that we have over here, the number of misclassifications that we have in a particular class is equal to the number of observations that we have in the class minus the number of good classifications that we have. So therefore, we can also write it like this thing that we have over here. Well, then again, very trivially, you should realize that this is by definition equal to this N1 mjs that we have over here, but not only this one, but also that one that we have over there. So we can therefore also write it like this. And then it's immediately clear that what we have here is 1 minus this thing divided by that thing. So we can then take this out of, well, we can make very large parentheses and write it in the way that I have right now. Well, then what I'm going to do is then again going to do quite trivial steps with respect to this thing over here. Here we will essentially take the sum over all those observations that are going to be in this particular subset. Well, we can do that also. We can also take a sum over the total observations that we have in our training sample. But then what we need to do is that we have to include then here an additional, well, indicator function that is going to indicate, of course, that xi must be in our subset. Well, again, this is quite trivial. Another thing that we can do is that we can rewrite this thing that we're over here exactly in the way that we had it before. Well, this is all quite trivial, but you should realize that now what we have over here is something that we have actually at the previous slide. We have defined it at the previous slide, because at the moment that we're going to scroll back to the previous slide, then you should realize that this is exactly equal to this p hat 1mj. But in this case, it's not going to be evaluated in this class, general class j that we have over here, but it's actually evaluated in c hat. So therefore what we're going to get there is p hat 1m c hat. So that's exactly what I'm going to do next, is that now I'm going to write this as p hat 1mc 1 hat. But then you should realize that c1 hat, well, that's actually 2 slides back, so you realize that that one was defined as being the thing that actually is going to maximize this thing that we have over here. It's the argument that is going to maximize this thing over here. So that implies that if I'm going to evaluate this in c1 hat, well, then it's just the maximum over all those p's that we have. So there we can simply also write this as the maximum over all p's. So that means that we can actually rewrite our minimization problem. Remember that we had these 2 sums over here, but the first sum can now be rewritten in this way that we have over here. The second sum we can simply rewrite it like this one that we have over here. So we can also write our minimization problem like this. In function that we have over here, and the one that we have seen earlier for the classification case. However, what we should realize is that this minimization problem, or at least this criterion function, is a little bit more intuitive. And that's immediately clear at the moment that we're going to ask ourselves the question, what is going to happen at the moment that one of these p hats that we have over here is exactly equal to 1? Well, then you should realize that, well, since that is by definition then going to be the highest outcome, and in addition to that we should also realize that since the sum of these p hats that we have over here is equal to 1 itself, so that means that the other p hats should be then equal to 0. That means, of course, that this maximum over here is then going to be equal to 1. That means, of course, that we're going to have 1 minus 1. So that means that this whole term is going to completely drop out. But we should realize that that does make sense. Because at the moment that we're going to have a situation in which this p hat for one particular class is going to be exactly equal to 1, then we have something that we already have seen before, and that is so-called pure node. Then we have, say, one particular subset that has only observations from a particular class. And we do already know that such a particular subset is very easy to predict. What we are going to have is a perfect prediction with respect to that subset, because of the fact that the only thing that we have to do is we have to, well, classify all the observations as exactly that class that we only have in that particular subset. Well, that gives us a perfect fit, and that means, of course, that the loss or the risk that we are going to have over here should be equal to 0. So that means in general that we can say that at the moment that we are going to have a situation of a pure node, so at the moment that one of the p hats that we have over here is exactly equal to 1, well, then we are going to generally have a large reduction in the total training risk that we have over here. That's especially the case at the moment that this n that we have over here, the number of observations in that particular subset, is relatively large, because of the fact that if this thing is large, then this thing must be actually small. So that means that the remaining training risk that we have over these classes, by definition, should generally become very small. So that means in general that at the moment that we have a pure node, at the moment that one of the p hats that we have over here is going to be close to 1, well, that's a very favorite situation. Of course, at the moment that p hat is not equal to 1 for one of the, well, different classes that we have over here, but it's close to 1, then still we are in a very favorable situation, and then generally we would like to have that particular class. But now let's look at a situation where it's completely different. Suppose that, well, the highest p hat that we have over here is actually relatively small. Well, then generally we will not be able to, well, predict that particular subset very well. In that sense, it's good to look at a particular example. Suppose that we have 5 different classes. And suppose that the highest p hat that we have over here is going to be equal to 30%. Well, that's of course not that large. And you should realize that that means, of course, that if we are going to look at that particular subset and if we're going to try to predict it, well then what we're going to do is that we're going to be, in 30% of the cases, we are going to be correct. Still, in 70% of the cases, we actually will make an incorrect prediction. Well, that's not that different anymore from, say, well, simply guessing. If we're randomly going to guess, well then at that moment in time, at the moment that we have 5 different classes, we will still have 20% of the cases, we will actually have the right prediction. So that means that at the moment that this thing is only equal to 30%, well then we are not able to improve that much with respect to, say, the remaining training risk that we have over here. So what can we say about this? Well, this means generally that what we would like to have is that we would like to split up this node that we have over here into two further subnodes, so 2 further subsets, for which the differences in the p hats among the classes are going to be relatively large. That we are going to do at the moment that we're going to look at this same measure that we have over here. But of course you should realize that we could also have used other measures of inequality with respect to the p hats that we have over here. One thing that we could have used is a so-called Gini coefficient, or the Gini index. The Gini index, generally speaking, is an index in order to look at the inequality, in this case with respect to the p hats that we have over here. That looks like this thing that we have over here. Apart from the Gini index, we could also look at the cross entropy or deviance. So that implies that, for example, at the moment that we're going to look at the Gini index, that we could have done also the, say, further subdivision by simply looking at this minimization problem that we have over here. Here I have replaced the original, say, minimization that we had before with respect to this Gini index. Well, there is a reason to use this Gini index rather than the original minimization problem that we had before. And the main reason is that the Gini index is actually differentiable in this p hat that we have over here. It's everywhere differentiable, including, of course, at 0. But the idea is exactly the same. At the moment that the p hats are going to be quite different from each other in a particular subclass, well then we like that particular subclass quite a lot. Therefore, we are trying to, well, break up the, say, space that we have into further subspaces, in a sense that we're going to try to find, well, subspaces for which the p hats are going to be quite different among the different classes. Okay, I would like to go on with the next topic, and that's the topic of bagging. What I already said in the introduction of this video is that essentially regression trees are generally not that great predictors, and the main reason why regression trees are not great predictors I already have said as well, and that is that regression trees usually have a very high variance. In that sense, it's good to go back to one of our earlier videos. In the second video, at the end of the second video, I said actually more or less the following, and that is to say that every, well, risk function, the theoretical risk function, maybe better to say the estimated theoretical risk function, well, evaluated at least in our estimator, can always be subdivided into 3 different things. First of all, we have the so-called unavoidable risk. Well, by its name, it already suggests that we cannot do too much about that particular risk, so we shouldn't care too much about that part over here. But in addition to that, we have the so-called squared bias. Well, typically what we're going to look at is the expected squared bias, and we have the expected variance. And what I said at that time is that the higher the bias is going to be with respect to a particular predictor, then we should realize that the risk, the theoretical risk, is going to be higher. So therefore, by definition, we're going to get a less good predictor. The same is true for the variance. The higher the variance is going to be, well, the worse is in a sense going to be our predictor. So that means that generally what we would like to have is a low squared bias and a low variance. Well, now you should realize that the squared bias, or the bias in general, with respect to regression trees is not such a big problem. You could actually see regression trees as a local method, so therefore generally in local methods, well, the bias is not such a big problem. But the variance is problematic in regression trees. And the reason why trees have a high variance is because of the greediness. We have already seen their greediness before, and you should realize that at the moment that we're going to make a particular split, then that particular split could be based on only a few observations, or maybe even one observation. It could in the worst case be possible that only one observation actually is going to, well, change the root node. That is to say that the root node would have looked completely different, in a sense that we would even have done the split, say, on an even completely different dimension with respect to the feature space. At the moment that that observation that we have would not have been there. So that means that the, say, predictor could actually be based only on one particular observation, and that generally is not that great. The reason behind that is because of the fact that that of course implies that we are going to have a pretty high variance. Well, now the question of course arises, what could we do about that? Well, we could do something about that in the case that we would have had B independent training samples. If we would have had theoretically a situation in which we would have had B independent training samples, then what we could have done is that we could have then looked at all the different trees that we're going to get from these B independent training samples. So we're going to then get not just one tree, but we can get B of them. So if, for example, B is going to be equal to 100, then we're going to get 100 trees. Essentially, we also get 100 predictors. That means, of course, that in a regression context, in the case that we would have had a continuous outcome variable, well, then what we could have done is simply take the average of all the different predictors that we're going to get from these different B independent training samples that we've over here. And then what we're going to get is something that we typically call a meta prediction. We're going to get a new prediction out of all these predictions that we have over here. Now the question of course arises, how large is the variance of that particular meta prediction that we're going to get then over here? Well, the answer to that is that the variance will only be a vector 1 over b based on the original variance that we had. So that means that we are going to reduce, in effect, our, say, variance by quite a lot. The moment, again, that b is going to be equal to 100, that means, of course, that our variance is going to be reduced by 99%. It's only going to be 1% of, in a sense, the original variance that we had. At the moment that we're going to look at the standard deviation, then it's essentially only going to be 10% of the original standard deviation that we had. So that is of course a big improvement, and we should realize that even in the case that we have a predictor with a very high variance and therefore might not be such a great predictor, at the moment that we're going to do this, then our final meta prediction might actually be very, very good. However, there's one problem, and that is that generally we do not have B independent training samples. What we typically have is just one training sample, and based on that we actually have to just look at one particular, say, trees, one particular, say, predictor that we have. However, well, what you could have said is, of course, what we can always do is that at the moment that we're going to have a training sample, suppose that our training sample is relatively large. So suppose that we have a training sample of 10,000 observations. Well, then what we could do is that we could sample actually without replacement from, of course, the training sample. What we could have done is get, say, 100 different independent training samples by simply, well, sampling from the total training sample of, in this case, 10,000 observations, and then sample 100 new independent training samples, which are going to be of size 100. Well, you should realize that the idea is pretty good with respect to this, but this doesn't work, of course, because of the fact that you should realize that then the final predictors that we're going to get based on our, say, trees that we're going to construct, these 100 trees that we're going to construct, they will of course have a much higher variance than the one that we would have had at the moment that we would have used all the 10,000 observations to build just one tree. Actually, we're not going to gain anything with respect to that, because of the fact that you should realize that these, say, individual trees that we're going to get out of the 100 observations rather than the 10,000 observations that we used, well, they will actually be having variances that are 100 times as large. Well, of course, at the moment that we're going to then, well, do this meta prediction, then they become 100 times as small, of course, of the original trees that we have been looking at. But we do not gain anything by just, well, instead, essentially doing one tree on all the 10,000 observations that we have. So therefore, we are not going to gain anything with respect to that. But we can do something instead. What we can do is that we can instead try to find surrogate additional training samples. We can do that by using backing. Backing is a method that provides these training samples by bootstrap resampling from the original training sample. That means nothing else as that from the total training sample that we have, remember that I denoted that by this T, this calligraphic T that we have over here. What we can do is that we can sample with replacement in order to obtain a bootstrap training sample that we have over here. So instead of that we are going to do it without replacement, we are actually going to do it here with replacement. Unfortunately, by the way, with respect to the notation that we have over here, unfortunately bootstrap sampling usually uses this star that we have over here. So this star doesn't now come from the fact that we do something optimally, as we have done so far, but this star actually comes from the fact that we use here a bootstrap training sample, this thing we have over here. And then what we can do is that we can do exactly the same thing as what we thought about at the previous slide. What we're going to do is that we, from these bootstrap training samples, we are going to build trees. So now we're going to have, in total, if we're going to have capital B of these bootstrap training samples, we are going to have capital B different trees based on those bootstrap training samples. And we can take the average now over this, and then we get the so-called backed predictor. We should realize that this essentially works exactly the same as what we had at the previous slide. Well, this is what we could do, of course, with respect to regression. In the case that we have an outcome variable that is continuous, we should realize that that cannot be done, of course, in the case of classification. But then, again, what we can do is that we can look at the committee vote. The class which is chosen, well, which we actually observe the most, that is going to be chosen as being our final predictor. Well, one important note with respect to backing is that the bootstrap samples are actually not independent from each other. So what we started with is looking at independent training samples. Then we have seen that the reduction with respect to our variance is going to be, well, reduced by a factor 1 over b. You should realize that that actually is not true at the moment that we're going to do bootstrapping. And the reason behind that is because of the fact that the bootstrap samples, they are not independent from each other. They're certainly correlated with each other because of the fact that you should realize that in many situations they actually have exactly the same observations. So therefore, they are not uncorrelated with each other. So therefore, also not independent from each other. That means in general that the reduction in the variance is going to be lower than this factor 1 over b that we have over here. Well, how large the real reduction is going to be, well, that actually depends a lot on the actual trees. At the moment that we are going to see that most of the trees that we're going to predict with respect to bootstrapping are almost identical to each other, well then at that moment in time the reduction is going to be very, very small. So therefore that means that backing is not going to be a very good method in terms of using them for regression trees, at the moment that the regression trees look all the same.